Hey guys, Squiv the Lazy Geek here, and today we're going to actually check the calibrated frame that I created in the last video with that dark and also bias at the same time calibration really. And we're going to try to estimate from it the amount of both signal from the target and any sky glow that came through my H-alpha filter. Then we're going to estimate the actual shot noise from those two sources combined, and we're going to compare that with the read noise of my camera. Okay, so first things first, let me look at my camera characteristics, and for that it was a 1600 mm cool, which has the same sensor as the 1600 mm Pro, so those charts here should be accurate. Now for me, I wanted to limit the exposure time that I was doing, and so my gain was 200. So I was not at unity gain, I was past unity gain. So I can see that at gain 200, my read noise is roughly like 1.4, something like that, maybe 1.45, something like that. So let me put that in a spreadsheet that we have. Read noise is 1.45, which is in electrons, right? So that's kind of the amount of uncertainty that's on top of whatever bias offset that we're having in the camera. Excellent. So now we have one good thing figured out. Now, by the way, about gain 200, one of the questions that I've seen and something that also has stumped me when I was starting is I see that read noise diminishes with gain, but when I take a picture at high gain, I see more noise in the image than what I see when I take a picture at low gain for the same exposure time and the same temperature of the sensor and the same offset. So what's going on? Why am I seeing more noise in the image? Well, you're seeing it perceptually, but there is not more noise in the image. The reason is that your ADUs, like going from one ADU to the next requires much fewer electrons, right? Because we are here, we have fewer electrons needed to go from one ADU to the next, which means that your sensor is more and more sensitive to any random noise. So any random noise will be visually overrepresented in that high gain image versus a low gain image where the noise that's caused by read noise, thermal noise, and also shot noise will not be that obvious because it doesn't make jumps of so many ADUs at the same time, whereas where my gain is high, all of those noise sources will make the ADUs jump around much more because each ADU is much more sensitive to electrons. So that's why you're seeing more noise with higher gain than with less gain. But it's really perceptual because the signal, is also having the same effect. The signal increases the number of ADUs that are triggered by that signal. So the signal has also grown, and just like before, the signal has grown linearly, whereas like your shot noise is actually growing as a square root function, and we'll see where that comes from in this video. So that's something to keep in mind. Like when you're increasing your gain, visually it looks like you're having much more noise. It's only because you are increasing the sensitivity of the camera so that the jumps from one ADU to the next are much more sensitive to the absolute amount of noise that there is in electrons. So here we are. So that's one thing. Okay, so I've estimated my read noise, and now we're going to estimate my my sky glow, so both from light pollution and the actual signal from the target object. And it's fairly simple to do, and it's an estimation, but we have our light frame that is calibrated from the dark frame, and I'm just going to go ahead and look at the average of that light frame. The average of that light frame should be it should be the amount of light that reached my sensor. Of course, there is deviations that are caused by the source of noise, but overall, it should give me a good idea of what we have. So I'm going to take my statistics in PixInsight. We're going to look at master dark calibration. And one thing you might have noticed that I have set my scale here to be 12-bit. So that it kind of matches the camera analog to digital converter. Because if I look at here, my ADC is 12-bit for this camera. So I'm just making sure that I'm comparing apples to apples by doing that. And we can see that both the mean and the median are roughly 55, 56. So I'm just going to say that my signal strength is on average across this whole image 56. So let me put that in the image in my spreadsheet somewhere, that we have like signal plus sky glow per subframe, or for my particular subframe, is 56, right? So 56 ADUs. So the unit here is ADU. Okay, so I know that's ADU, but I want to actually convert that to electrons so that I can then get my actual shot noise from that. Okay, so let's convert that to electrons. To convert that to electrons, it's simple. We know what the gain was. So I go back to these charts and I look at my gain 200, and I go up and I look at my electrons per ADU. And my electrons per ADU, it seems to be roughly 0.5, maybe 0.45. Let's put 0.5. So we're gonna put here that gain in electron per ADU is 0.5. Good. So now we know in electrons the average of my signal across the frame for this single exposure will be single exposure signal and sky glow in electrons will just be this value, 56, multiplied by the gain in electrons per ADU. So we have 28 electrons. And now I'm going to do something that has always stumped me about how people would be sure that shot noise was equal to that. I'm going to say that the shot noise, and I'm actually going to put it next to the read noise here. So shot noise in electrons is the square root of this. Okay, I'm going to put square root as of my signal. And I keep mentioning in my videos that my shot noise increases as a square root function. And it is exactly the square root of the signal, which includes the light pollution. Okay, but why? Right? That's why can I just take the square root of the signal and say it's my shot noise? And the answer to that is it comes with statistics. So you model, we have our buckets, our pixels receiving photons. Photons have a certain average rate at which they hit each pixel, right? On average, we know that we'll get a certain number of photons, or if we go to the electrons that we measure from the photons, a certain number of electrons per pixel per second, on average. But from 1 second to the next, that number will be like maybe above average, maybe below average, etc. And so we want to know the shot noise will be like overall in the majority of cases, and actually strictly speaking in 68% of the cases, between which two values are my electrons measurements contained versus the average. And that's determined by the square root. And that distribution that models that is called a Poisson distribution. And if you remember from high school statistics or probabilities, you might have had a problem asked you about, like, okay, I flip a coin five times. What is the probability that we had exactly 2 times heads and 3 times tails? for that experiment. And you learned about something called a binomial distribution that had a nice formula that came out of it, and you could find the probability by just applying that formula. And actually you can take that binomial distribution, you can kind of tweak it. You don't really tweak it, you just take a special case of that binomial distribution, and you can actually make it become a Poisson distribution, which models our shower of photons onto a pixel, or our raindrops into a bucket. And once you've actually made that math, done the math, and you've gone to the Poisson distribution, you're gonna measure the mean of that distribution, so the average, which is what we measured here of 56 ADU or 28 electrons, and then you're gonna measure the average deviation, so the standard deviation, like, you know, that you get between each exposures of X seconds or 1 second, and you're going to see mathematically that it is equal to the square root of the mean of your signal. And that's where it's coming from. It's mathematics, it's the model we have for electrons reaching a sensor or a pixel, of photons reaching a sensor or a pixel. And you know, you can actually do exactly the same thing. The Poisson distribution is used for a lot of applications in daily life as well. And it's a very neat thing to know that the random part of that distribution, like the noise itself, it can be modeled by the square root of the average of your the amount that you received. So here we are. We know that the shot noise is the square root of this in electrons, and we have it. So let's now simulate roughly a 10 by 10 sensor. So I'm going to add some columns here, and we're going to say that this column will represent the deviation from what the sensor value should be because of the read noise and read noise impact. And then we're going to see the same thing for the shot noise impact. And for that, I'm going to use a function from Google Spreadsheets here that is just saying, like, okay, Google, dear Spreadsheet, please give me a number that is close to an average of 0, but that will be kind of within this read noise, within plus 1.45 and minus 1.45. And sometimes it can be higher, sometimes it can be lower, but most of the values, and more precisely 68% of the values, should be between 1.45 and minus 1.45. It's possible to do that, and to do that we're going to use a spreadsheet function called normsinv. You don't need it goes back to distributions and normal distribution. You don't really need to bother with the details, and we're just going to multiply that by the read noise, and we can drag that down for roughly 100 cells, and that will generate random numbers. Google Spreadsheet has generated for me the impact of the read noise of on my sensor, you know, by magic, by mathematics. Okay, and we're going to do exactly the same for the shot noise, and then we're going to add them together to see what the total noise impact is. So we're going to add, we're going to also simulate the shot noise, and it will be exactly the same. I'm going to copy this formula, except that instead of using my read noise figure here, I'm going to use my shot noise figure, which will be B2. Here we are. So now we are simulating my 10 by 10 kind of sensor in terms of the noise impact that is on that sensor. And now we're going to just add those values together, and we're going to set total noise. And the total noise impact, we're going to measure it in the end in terms of an average electrons value, just like we did for read noise and shot noise. And we'll see it is not equal to shot noise plus read noise. It will be closer to shot noise than the sum of those two. And we'll see why. So we have read noise impact, we have shot noise impact, and you can see that for some values, the read noise and the shot noise are working together. So if I take the sum of this and that, so I'm going to do this plus that value, and validate, and we're going to drag that down the whole way. We can see that sometimes it gets, it works together. So the read noise and the shot noise here, they're both positive values and they're adding themselves on top of each other. Here they're both negative values, they're adding themselves on top of each other. But here, for example, the read noise has a positive impact on my pixel, but the shot noise has a negative impact on that pixel. If they were exactly equal, the noise would actually cancel itself out from those two. Interesting. So you can see that the total noise impact on that particular pixel is in absolute value lower than either source of noise. And that's where, like, intuitively you can think like, oh right, so it's not a simple addition. And so now we've simulated my sensor, and we've simulated, one exposure, let's say, on that sensor. And what I'm going to do is I am going to say, like, to ask Google, okay, from that simulated sensor with those two sources of noise, with the impact of those two sources of noise, what is this value? How can I measure this value in terms of just a simple number of electrons? And so we're going to ask Google, like, hey, I want to be 68% sure that what value would I have so that I'm sure that 68% of the samples in this total noise impact will be between plus that value and minus that value. It's exactly the same criteria that we used for the read noise here and the shot noise here. So this way to do that is just the standard deviation. So we're going to have the total noise, and we're going to say that it is equal to the standard deviation of this. And standard deviation is just a tool. You don't really need to know how it works. We're just gonna take it, and we can see that in this particular scenario, for this one exposure on my 10 by 10 kind of pixel sensor, it is 4.9. Okay, let's remember that. So I'm going to copy paste that, and you'll see that each time I copy paste, Google, the spreadsheet, will actually simulate another exposure on that sensor with another, completely random element to noise. And we're going to then average all of those measurements that we get. So one of those measurements was 4.9. So I'm going to copy that in this column. This next one, you can see it has been renewed. We did another virtual exposure with my my spreadsheet sensor of 10 by 10 pixels, and I'm going to copy paste that again. And we're going to keep doing that for a certain number of times, and then we are going to average that out to see, across many exposures, what was my my average noise in total caused by both my shot noise and my read noise. Okay, so now I have actually 30 samples, right? I've simulated my my sensor with 30 different exposures, and we can see the impact, the total noise impact here is measured in all of those measurements here. So I'm just going to take the average of that, and we're going to say, like, total noise. We're going to call that total noise in electrons, and we're going to say that it's just equal to the average of all of these values here. Okay, and we can see it is 5.4 in this case. So there's actually a margin of error, because you can see that all of those values are slightly different, right? So the more samples I get, the closer I will be to the real total noise value that I'm having. I believe this is using a very powerful theorem in statistics and probabilities, which is called the central limit theorem. We don't need to go into details, but the more times I simulate my sensor, the more accurate this figure will become. Now, this figure, it so happens that I could do something else. I could take the square of this and the square of this, add them together, and take the square root. So let's try that. And here we are. This is the result of the absolute calculation based on the square root of the sum of the squares of this read noise and shot noise. And you can see it's a surprisingly close value to the value that we got via our simulated sensor here. So very interesting to see. So now you can see kind of where these sums of squares that you see in Robin Glover's videos are coming from by actually simulating the sensor and seeing the total noise impact. But what we can see very clearly here is that the contribution of the read noise versus the contribution of the shot noise is, you know, the read noise contributes very little. It's like we're just like 0.2 electrons, even less, 0.2 electrons above shot noise. So that means it gives me a good indication that I am likely swamping my read noise with my particular exposure time that I got, right? So I can actually measure that after the fact. And if we want, we can actually look at Robin Glover's formula. So here we are. We can see that the recommended sub length or the optimal sub length, but again, as I mentioned before, you can go beyond that with pretty much no negative effects unless you're saturating some of the pixels. It's 10 times the read noise squared divided by the light pollution rate, which is in electrons per pixel per second. And the light pollution rate, I'll include my signal rates. And I think it's fair because the shot noise is generated by both the signal and the light pollution. And in Robin Glover's presentation, he very often seems to include, as far as I understand it, the sky glow or the light pollution, or the signal of the object within the sky glow or light pollution, at least from the formulas that I've seen on his slides. I may be wrong, but that has been my understanding. So what we're going to do is we're going to say, okay, we need to know the read noise in electrons. So we already have it there. So this read noise squared. And we need to know the electrons per pixels per second. Okay, so for that, we know that my exposure time was 480 seconds, and that on average, I got 28 electrons per pixel, right? So I'm just going to get my rate in electrons per pixel per second will be 28. So this divided by 480. Excellent. So now we are getting a bit closer to everything, and we're going to find our ideal or optimal exposure lengths. And we're going to follow exactly the formula from Dr. Glover, which will be 10 times the read noise squared. So I'm just going to multiply the read noise twice, and we're going to divide that by my electrons per pixel per second rate, which we have here. And it tells me that my optimal exposure time would be 360 seconds. Now, of course, there are uncertainties there. You can see that just by looking at those charts here, sometimes it's getting very ambiguous. I have to kind of estimate where this dot really is. So I should be using, well, Dr. Glover's own sharp cap to measure the sensor data, for example, and get actual proper figures. I also used a single light frame, and we know that the average of that light frame might have been affected by the noise itself. So my measurement of the sky glow and signal together is slightly off, very likely. But still, it gives us a pretty good idea that my 480 seconds exposure is actually not a bad thing. I am exposing above the optimal exposure lengths, so I am definitely swamping my read noise. At the same time, I am definitely not overexposing. I am not saturating any stars. So my exposure of 480 seconds, it just works well for me, and it gives me a very good safety margin on top of this optimal exposure length. So that was a long video, but we've simulated a sensor, we've simulated noise on that sensor, and we've proven to ourselves how this noise adds up together, and then we've actually double checked our optimal exposure lengths. And I think that's pretty cool, and I'll call that a win. So I hope this was useful or interesting to you guys. It's a very practical kind of thing to do. So I hope this was useful to you guys. I think to me it was super interesting to actually see that actually working. And you know, if you like this video, please click like. Please also don't forget to subscribe to this channel. There's tons of good new content coming up, both very technical like this one and less technical like reviews of some equipment. And you know, always don't forget to look up at the stars, and I'll see you next time.